Hello, everyone. Welcome to MEERTALK. My name is Kaeza Fern, and I'm the Director of Communications at MEER. We are so happy to see you all here on this beautiful day. And why don't we begin with just taking a moment of gratitude for Earth, for all the living creatures who have passed by maybe this very spot that you're on over time. And I invite everybody to begin with a deep breath before we dive in to a lot of great material for today. Today, you'll be hearing from a few people who are involved with MEER, and we want to invite you to donate to help financially support students both at Plymouth State University and at a couple of locations where we are going to be doing field tests. So to do that, you can go to MEER.org/donate and make a donation. There are various kinds of help that we'll need, including housing a couple of students who will be conducting research in New Hampshire. So we do appreciate anything that you can do. And I will put that link into the chat for you. So MEER.org/donate. We will have 3 10-minute or so presentations, starting with Dr. Ye Tao, then Peter Dynes, and after that, Lisa Donor and Eric Hoffman. After each of the talks, there will be a short question answer period. And if you would like to ask a question, we invite you to just write that into the chat. And please do be brief and to the point. It will be a short chat period following each presentation. So we're going to begin with Dr. Ye Tao. Dr. Ye Tao is the founder and director of MEER. MEER is for Earth's Energy Rebalancing. He received a doctorate from the Department of Chemistry at MIT in 2015 and completed the research requirements for a doctorate in physics at ETH Zurich. He led a research lab at the Roland Institute at Harvard, and in 2021 left the institute to devote himself to the singular task of bold and creative engineering solutions to the problem of increasing heat on the planet.
All right, thank you, Kaeza, for the introduction. And thanks to everyone for joining us today to this event. And you have all been supporters of our initiative. And it's really great to see all of you here. So today I'd like to start by saying happy holidays to all the laborers and all the workers in the world that's keeping the lights on for us. And from the farmers that feed us to the medical care professionals to keep us healthy as individual persons, and also the scientists that's trying to diagnose the current ongoing global warming disease for the planet. We have to really thank them for all their work. And we also have to remember that underneath and supporting all of these workers is our Mother Earth. And she really enables the production of all the plants and animals that we depend on for our life and existence on this planet. So we have to also pay tribute to Mother Earth and all the producers. So today's talk was motivated by the observation that in spite of a reduction in emissions in 2020, we somehow experienced seemingly a lot more natural disasters during that year. For example, we had a record 30 named storms in the Atlantic, and the hottest land surface temperature was also measured in the same year. And also in parts of Asia, there was really a record raining and flooding observed during 2020. So it's a little bit counterintuitive, perhaps for most people. But it's really not that surprising for people working on climate change and human and natural systems, because all the different components are intimately connected through very complex networks of interactions. And for the purpose of today's discussions, we'd like to focus, first of all, on how a change in the emissions of greenhouse gases and pollutions from the different things that humans do, including moving around and producing the things that we need to consume and eat, to how that could impact temperature. And in turn, how both temperature on land and in the waters, in combination with perturbation of cloud condensation nuclei or pollution, can impact the water cycle, leading potentially to extreme climates that include storms and flood. So COVID, from the perspective of climate scientists, can be conceived of as an experiment. So here's the logic behind such a fortuitous experiment. Humans emit different sorts of emissions, including long-lived greenhouse gases, represented here in their warming magnitude by this red arrow. There are also short-lived pollutions that really they don't last for very long, generally a few days. When you have a precipitation event, then they're washed out of the sky. So under normal, quote unquote, default circumstances, the two components add to give a net forcing which is smaller than what you have if you only had the greenhouse gases. In one hypothetical scenario where we, let's say, succeeded in transitioning completely to renewable energies, we would not have pollution anymore. And as a result, we would have a net warming forcing that's much higher than we currently are experiencing. And in the year 2020, as a result of temporary reduction in pollution or emissions, what we had was, during a certain month or episode, a reduction of on the order of 1/3 of the amount of pollutants in the air. And the result, we had momentarily an increased amount of net positive forcing, which could have led to downstream consequences for temperature and climate and extreme weather. So first of all, I want to reemphasize that these long-lasting greenhouse gases were very minimally perturbed as a result of COVID lockdowns. So in fact, we would have experienced a lockdown that's 4 times as severe in order to be even measure the difference. So for all intents and purposes, greenhouse gases were negligibly impacted. And we will show later in some data that colleagues have produced that it's also borne out in those analyses. What about the cooling component? So before the experiments that were enabled by 2020 events, we had a pretty good idea of how much they were cooling the Earth. So the radiative forcing due to these emissions were on the order of 1 watt per meter squared. And in order to convert this rather perhaps awkward unit to a temperature unit that most people can understand, we can multiply this number by a factor which carries the unit of degree per watt per meter squared. So the units cancel, giving you an expected cooling of about 1 degree Celsius. So let's see whether the events of 2020 are consistent with this order 1 degree of hidden warming. So when you experience more sunlight, the extra sunlight can be converted into heat at the ground via absorption. And the thermal energy on the ground or in the oceans can manifest either as increasing temperature or as evaporation in the form of latent heat. The temperature on the soil or in the oceans can warm the air above it and creating turbulence and convection and a movement. And the combination of air movement and transport of moisture is what's behind the formation and transport of moisture over land and the production of rain, and in severe cases of extreme flood. So question number 1, did we actually experience or receive more sunlight on the ground as a result of lockdowns? there were several experiments taking place in different parts of the world. And in the case of India, a rather polluted area, after the start of lockdowns around the 21st of March, there was a dramatic increase in the amount of sunlight received compared to the average of previous years. The increase was very dramatic. In fact, it was like 8%. And as a result, solar photovoltaic production also increased proportionally. So that's one potential benefit of cleaning up the air, making the solar energies more efficient. But from the perspective of controlling temperature, it's the other way around. And in terms of numbers, in March 2020, the local radiated forcing change on the ground was about 20 watt per meter squared, a rather big number. Elsewhere on Earth, for example, in Europe and also in rural and coastal Asia, where the concentration of pollutants was not as extensive concentrated, the amount of change in solar irradiance reaching ground was more modest, but still we measured on the order of a couple watt per meter squared increase in different locations. And in the case of the Netherlands, measurements really indicated a extremely high level of 206 watt per meter squared, way above previous records. And if we look at just the distribution of the direct component, it's really highly unlikely for such an event to have occurred without something extraordinary, such as the lockdowns. Okay, so the data seems to be consistent with an increase in shortwave radiation reaching the ground, and how much you get is pretty much location dependent, also depending on local background pollution levels and how much and how long the lockdowns were. Now, the next question, did the temperature actually increase as a result of more sunlight? The most analysis to date has been concentrated on mainland China because it's one of the first places to institute lockdown measures. So scientists had the data earliest. So several studies emerged and they pretty much agree on a land temperature warming on the order of 0.5 degrees Celsius plus minus 2. And I want to point out that in this particular experiment down on the bottom right corner, simulations indicate that the aerosol component led to on the order of 0.3 degrees Celsius. So part of the difficulty in really nailing down the aerosol effect is these measurements and also simulations are riding on top of background synoptic, basically weather variation. And you have a lot of natural variability, and to tease out the aerosol component is the main challenge that has made giving a precise number in this field rather difficult. But within the right order of magnitude, the data seems to be consistent with our prior understanding of the magnitude and severity of hidden warming. Another thing to point out is that current generations of climate models, Earth system models, have a pretty difficult time really pinpointing the aerosol cooling, aerosol masking effect. And in general, simulations that are informed by observations predict higher levels of warming compared to simulations that are purely based on only model inputs. And as a second part, let's look at whether there's indication of downstream extreme weather event as a result of land warming. A recent study that came out a couple of months ago tried to investigate the rainfall in this region of mainland China in the past few decades. And as you can see in this graph, that the amount of rainfall in 2020 cannot really possibly be a result of natural fluctuation, unless it's a one out of maybe it's less than sub 1% event if we model this data, say by normal distribution. So it's really highly unlikely. So the researchers then tried to tease out the different contributors to such a rare event. What they found was that if we only changed the aerosol amount in the models based on our best understanding of what happens as a result of lockdowns, then we can explain about a third of the precipitation anomaly. If we also included greenhouse gases, CO2 emission changes, the results are not significantly altered. That's because the concentration change of CO2 is really negligible because we have such large stock of it already in the atmosphere. So that basically confirms what we mentioned before, that the short-lived aerosol component is really behind or contributing the most to the observation. So in summary, the observation of 2020 was highly unlikely due to natural variability alone, and about a third of the observed anomaly can be attributed to aerosol reduction. And that the greenhouse gas, CO2, mitigation contributed negligibly to these extreme disasters. As people looked forward to what might happen following the pandemic of 2020s towards the 2050s, when we wish to become carbon neutral, it's becoming increasingly clear that the global impact of local radiative forcing will be different as different parts of the world clean up. And the most impact are expected in South Asia and the Southeast Asia, and also parts of Africa, essentially the frontline communities. So these results should really inform our political decisions and expectations for different nations in how quickly they're expected to decarbonize. Because incrementally, it really hurts those regions a lot more if they were to go carbon neutral locally first, compared to if more developed nations and areas with more means to adapt take the lead. So this topic should really help to inform future discussions among policymakers. And these pictures are basically from this past week. For example, Peter's talk will talk about extreme heat that's going on in India, the worst since more than a century. And this landfill really caught on fire due to extreme heat in the region. And looking forward to the next year within the MEER framework, we're currently looking at how to use the resources that are discarded in the landfills of the world to help make the MEERs to help counter global warming. And we find that 1/7 of the aluminum cans that we currently landfill are sufficient to provide the aluminum for making the MEERs. And if we were to make the substrate for these MEERs based on thin film PET recycled, we can more than satisfy our needs to arrest global warming. And in terms of glass, currently landfilled glass of various colors can satisfy 10% of the needs for making stands for our devices. And landfill emissions, fugitive emission in methane, similarly is sufficient for 50% of our energy needs for the MEER framework. And if we add to that the 88% that currently escapes the production and the distribution network, we can more or less have sufficient thermal energy to make our devices. And with that, I'd like to thank every one of you for your support and for attending this presentation, and I welcome questions.
Well, thank you so much. And I will introduce Peter Dynes, who will be speaking next. As Director of Strategy, Peter Dynes focuses on developing the organization's medium and long-term goals. He also heads up the MEER Urban Adaptation Project. With a background in environmental science, he was a London-based environmental consultant for years. He's also a director of several Irish cooperatives and general secretary of the Cooperative Party of Northern Ireland. So Peter, so glad to have you. Take it away.
Okay, thanks, Keza. Thanks for the intro, and thanks everybody for attending the talk as well. And thanks to Ye for that excellent presentation, even if it's a very concerning presentation about the aerosol effect. I've been asked to talk about the urban side of the project and what MEER is currently planning in urban settings. And so if it comes to the questions, if you're thinking of questions, I would save more technical questions for the likes of Ye to answer. If you want more questions about this type of project and what we're doing in this type of project, then I'm happy to field those type of questions. I'm not going to go into the full technical details either. I really want to concentrate just on what's happening currently on the ground and why there's an urgent need for adaptation. So firstly, just look at the world heat map for the March of this year. It was the 5th warmest on record, and that's in spite of a cooling La Nina year as well. In India, where 2 of our projects are currently based, the heat waves actually came earlier this year. So the heat wave season usually starts in about March, but actually this year, our colleagues over there have been telling us that it was getting very warm in February. And March was the hottest March on record. April also looks to be, if not the hottest, also one of the hottest on record also. So this is literally what's been happening in India over the past week. At times, virtually the entire country has been over 100 degrees F. Hold on, it doesn't like that. Okay, so in the last 6 weeks, New Delhi has averaged more than 4 C above normal. And for such a long duration, that's about as large a temperature above normal period that they've ever seen. We were told that this was years away, but it's actually happening at the minute. And with the heat comes other issues, and I noticed Ye actually showed something along the lines as well, but this is one of the biggest landfill sites in the world outside of Delhi. And it's currently on fire. This is the 4th major fire they've had in a matter of weeks. And the frequencies of these fires is increasing as the temperature is also rising. Large swathes of people throughout the country have been gasping for air in really, really uncontrollable heatwave conditions. And this was Karachi in 2015. And I mean, how long is it going to be until we start to see the bodies lining up again if we continue with these type of heat waves? In Kim Stanley Robinson's book, Ministry to the Future, he predicts serious wet bulb temperatures in India where millions will perish in a number of days. And it looks like this work of fiction could be closer to reality than we actually thought. So what is MEER Urban? So MEER Urban is a heat adaptation project. We aim to make buildings more livable in regions where people are suffering. And our focus is to build climate resilient adaptation for those who haven't got the means to do so for themselves. As Gutierrez says, adaptation will save lives, and without it, many people will perish. So what is our challenge? Well, heat kills more people than any other climate effect, and these numbers are currently on the rise. Currently, we have over 1 billion people with no means to cool their home at all. It feels like we're being cooked alive. We're cooking like pigs in here. This is Freetown. It's one of our partner cities. And housing made from certain materials like concrete and metal sheeting, etc., just makes things worse. So what are some of the impacts of all this heat? Well, women who predominantly work at home are seriously disadvantaged for a start because they cannot work within their homes. there's a number of serious health impacts as well, which I could go on for about half an hour about, like boils, etc., in children. Many people have to resort to sleeping outside as well because of the unbearable heat within buildings. And the infrastructure literally breaks down. Roads literally melt with the high temperatures, and we've been seeing that over the last couple of weeks in India as well. So what do we want to do, and how can MEER actually help? Well, what MEER actually wants to do is to install specifically designed solar reflectors on rooftops. And this can also be described as like passive cooling. In a nutshell, what this means is we want to increase the albedo on the rooftops and reflect more solar radiation away. So this is what a typical concrete rooftop looks like in India. And the concrete acts a bit like a battery. So during the day, it's storing all that heat energy. And then at nighttime, it's radiated inside the house as well, making it just really, really unbearable and really uncomfortable. And I was speaking to one of my colleagues this week, and he was saying it's literally 46 degrees during the daytime, and at nighttime, the nighttime temperatures are still around 35. So this is a mock-up showing what a MEER rooftop might potentially look like. And on the left-hand side there, you can see that these are specifically designed glass roof tiles for like rooftop patios. On the right side, you have a specifically designed polymer sheeting that we're working with engineers on. And with both, we think we will reflect around about 93% of incoming light. And we anticipate inside temperatures with these type of applications to be maybe up to about 6 degrees lower. And we're developing the prototypes currently. The sheeting applications could also be used in other settings as well, like depicted here in marketplaces, maybe over landfill sites as well, which we've seen that was on fire. Possibly you could cover landfill sites and you could cool them down, which might prevent the fire risk also. We see lots and lots of possible uses for these type of applications, and we're just getting started with our ideas. So how are we going to reach out, and how are we going to bring relief to people? Well, we're building a network of partners based in cities currently suffering from thermal intolerance. And for the purposes of our initial work, we've chosen Ahmedabad and Freetown to start our projects. So in Ahmedabad, we're working with Mahila Housing Trust, and they are specifically work to empower underprivileged communities. And this is where MEER wants to reach first. In Sierra Leone, we will work with Eugenia and her team at the Freetown City Council. And she's actually the first heat officer ever appointed in Africa. So why should those that contributed the least to climate change pay for the consequences? That's an essential question. And why should those with the smallest footprint suffer the most? The least we can do is to help people adapt to a world they didn't create. And finally, I'll leave you with this, that no matter what your current take on the climate predicament, no matter what your current view is on the climate, at MEER, we believe it's never too late to be humanitarian.
That sounds great. Thank you so much, Peter. We are going to move to our last presentation now, and that's with Dr. Lisa Donor and Dr. Eric Hoffman. I'll first just tell you a little bit about them. So Dr. Lisa Donor is lead investigator of MEER's field experiment, including materials acquisition, MEER design and setup, feasibility testing, and data collection. An associate professor of environmental science, her research at Plymouth State University is on detection of and education about climate change in the past and present, as well as future. So, Dr. Donor, thank you so much for being with us we look forward to what you have to present. And along with that, I will also introduce Dr. Eric Hoffman. Dr. Eric Hoffman has been a meteorology professor at Plymouth State University for over 20 years. His main areas of expertise are developing short-term climatological analyses of weather and weather events with some experience with making field measurements. So we look forward to hearing from both of you.
Yes, so Dr. Hoffman and I have been working together with Dr. Tao on this for over a year now, working to get this idea fleshed out and funded to the extent where we could start implementing and answering some of the questions that we have. So we've received funding already from various New Hampshire state institutions, including Plymouth State University, the New Hampshire Technical Institute, and Keene State College. We've also been able to leverage New Hampshire IMBRI in order to provide student support for last summer, and the National Science Foundation, which continues to provide support for materials and also student internships on this project. Now, I wanted to go a little bit into how climate change manifests itself through greenhouse gas emissions, but also the balancing effect of the reflectivity. This is a scenario created, it's a program called C-ROADS, and you can go onto it. It's cheap, it's available. It was created by the Intergovernmental Panel on Climate Change in order to educate politicians, decision makers, and the public about how these complex climate interactions work with each other. So in the left panel, we see the greenhouse gas net emissions all over the globe, projected using data from 2000 and projecting 100 years forward to 2100. And on the right side, we see the response of the climate in terms of temperature in degrees Celsius, with that business as usual kind of scenario where we're not making any changes in emissions and we're not implementing that transition that we need to do away from fossil fuels. So this is kind of the worst case scenario, but you can see that what happens is that we are currently still in what's considered a relatively safe range of temperature, despite what we're already seeing with climate impacts, okay? So, you know, those issues with the temperature extremes that we're seeing already in this year, that's considered safe, all right? So this is the perspective to have. Once we get above 1.5 degrees Celsius, we enter what most scientists would agree is a relatively high risk range that we would like to avoid if we could, but that includes, you know, enhanced effects of sea level change, coastal flooding, intensification of storms, intensification or lengthening of the storm season, especially the hurricane season. And then above 2 degrees, we are really in what most scientists would agree and modelers are projecting to be a catastrophic or devastating range of temperature change. And to give you some idea, 4 degrees increase in temperature is the entire difference in global temperature between the height of the last ice age, when there was a mile-high ice over much of the land masses of the northern hemisphere, and now. All right, so 4 degrees temperature change is that type of scale of difference. Now we're talking about adding 4 degrees in the other direction, warming. So we have not lived through that kind of change. We don't know what it's going to bring, but we can project some of the indications of what's going to happen. And that's what these models are really being used for, is to give us some idea of what it's going to look like. So we can use this same model to do some what ifs. You know, what if we actually start implementing some changes in our greenhouse gas emissions? And what if we change the amount of deforestation and the amount of new trees that we plant? And so I ran this. It takes just a few seconds. On anybody's computer can do this. And if all of the developed nations within the next 8 years come to an agreement about how they're going to manage their gas emissions, and they can peak their total emissions in 2030 and then reduce them by 5% every year thereafter, and prevent all trees from being cut, and reforest all of the areas that are possible to be reforested. And then in 2050, if the developing nations, which economically need a chance to develop somewhat in order to get out of their levels of extreme poverty, they need the benefit of that energy that's been available to the rest of us in order to advance their civilizations. If we can convince them to develop strategies that allow them to stop and peak their emissions in 2050, and again, then afterwards reduce it by 5%, and again, no more tree cutting, total reforestation. What we see is that on the left, the blue line is showing that the emissions do drop, and they drop by 2100 almost back to zero, which is our baseline desired level, which is awesome. But we see on the right that the temperature response doesn't drop off as the CO2 drops off. And that's because the Earth's system has a lot of inertia. And we're also continuing to add gases to an atmosphere that's already experiencing an intensification of gases. So we've got a historical reservoir of gas, and we're continuing to add to it, even as we're trying to decrease the amount that we're adding. So that 5% reduction doesn't mean we're reducing the total amount of atmospheric gas, greenhouse gases in the atmosphere every year. We're reducing our emissions. So each year we're adding 95% emissions to the atmosphere, and every country is. This is why we see this increase in temperature, which is the blue line. And even with this really highly optimistic scenario that involves a lot of human behavioral change, we see that we're still in the devastating range of temperature after about 2050. We don't want to be there. So not to make it even more gloomy, but it does get even gloomier to some degree, because if we just look at the global emissions and we say, all right, let's say we peak emissions this year. That means next year, our total global greenhouse gas emissions are less than this year. And the year after that are less than next year, and reduce it by 5% every single year after this year globally. And we don't cut any more trees, and we plant as much land as possible in trees or other sorts of carbon storing material. We still are in the high risk range. So the point of this is to show you that greenhouse gas solutions alone are insufficient. We've already reached a point where this is no longer the only viable solution. We also are dealing with just what I call crisis fatigue, and a lot of hopelessness. A lot of people feel like solutions are beyond their control. You know, what can I do? Nothing that I have wanted or encouraged to do has made any difference. We're still on this trajectory, and we're worn out. We're all exhausted from this, right? I think we have to recognize that there's a limit to our capacity to push and push and push for solutions. With one caveat: if we had time to catch our breath between crises, time to develop ideas and convince people that this is really necessary, and to work out strategies for that to happen, I think that's where we can combat the hopelessness and we can combat the problem of fatigue. But we do need time. And so our project is, I see it as a way of creating time. We're slowing the pace of climate change. In order to understand how that works, some really fundamentals. You know, climate starts with solar energy. It's coming in from the sun to the planet, and the planet is responding. So as others have mentioned, some of this light coming in is reflected away it's reflected by clouds, it's reflected by aerosols in the atmosphere, it's reflected by bright surfaces on land like snow and ice, although those are becoming less each year. The rest of it is absorbed, and what's absorbed is generally transmuted into heat. And then that heat is what interacts with the greenhouse gases. So the idea of increasing the reflective surfaces is that we send light away before it becomes turned into heat and before it interacts with greenhouse gases. So it's a way of enhancing what's already happening naturally. And by doing so, we do actually buy time, because if you don't get that heating immediately, you lengthen the curve of the temperature response. So climate mitigation is this idea of trying to restore a balance by either increasing the amount of light reflected by the earth and decreasing the amount of heat retained by greenhouse gases. And these two mechanisms are outlined in the blue boxes here. So increasing the amount of light reflected by earth can be done by people by creating artificial reflectors, building things like mirrors. And there has already been proposals to shoot scattering elements out into outer space, to disperse them in the atmosphere. There's a lot of nervousness around these techniques because they affect everybody immediately, and we don't know all the consequences of these. But we can also do ground-based solutions to those, which is much more in control. So the advantage of tackling this problem by increasing the light reflection is that it doesn't rely on social behavior changes. It doesn't rely on politicians being won over and being convinced that climate change is a high priority on their list. But it does require technology, and it can be expensive. And often the highest tech versions require experts to install and to maintain it over the long term. So this is just a temporary solution that buys time, but it does not eliminate the problem of greenhouse emissions. It has to be done in conjunction with the second part, which is decreasing the heat retained by greenhouse gases. And that is primarily, has been proposed so far, is by reducing the emissions and by switching energy sources away from emitting sources, things like solar, wind, use less oil, but also, I think this is really key, everybody has to use less energy overall. We can't just depend on these other sources to substitute for our entire energy consumption each year. We have to have less consumption of energy each year, because these alternative sources really can't match what fossil fuels can do. The downside of this strategy is that you really do need a lot of cooperation. You need human behavior to go along with this, and it requires some technology. It involves regulations, it involves education, and it involves a lot of reduction in greenhouse gas emissions overall, and increased storage of carbon. We need to find places, we need to conserve land for developing those storage areas. So these two solutions are not competing solutions. They're working with each other. The reflective solution is to give us the time needed for the greenhouse gas solution. So in particular, our solution is to look at ground-based surface mirrors. So we are thinking of them as something that's mobile. It's very low tech. Anybody can implement it. In fact, the mirrors that we have to test with, I can hold the entire frame of that with the mirror on it in one hand, and I'm not a very big or strong person. These are relatively low cost. Most people and communities can afford them. They're easily repaired and they're easily replaced if they can't be repaired. They can be made from sustainable and environmentally friendly materials. And very important, it's easy to quit the treatment if it turns out it's having a negative effect, which is not something that can be done if you disperse things in the atmosphere or shoot it into outer space. So having that ground-based element offers a lot of control. And I think that's a comforting thing for people. The downside or the cost of this is that we need to scale it up. One array is not going to be sufficient. And we also don't want to pave the earth with mirrors, right? We don't think we're going to have to do that, but we do need to get global coverage with the idea of having arrays of mirrors in a lot of different communities. You know, I'm thinking probably an acre or less in size, but part of what we're trying to do is determine what is that acreage needed, how much area is needed in order to create the effect that we're looking for. It does need to be maintained locally, so there has to be buy-in and continuation of this through commitment by the communities or the people that are doing it. And we also have to know what's the impact on the soils and on the local plants. So, you know, our experiment is all about testing this concept and determining how many mirrors are really needed. And that's our goal. Eric, over to you. Oh, sorry, I had one more slide. The aspect of climate education. So the work that we're doing is the funding for it has largely been in support of the education component of it, because we can do a lot of outreach using our arrays and using our demonstration kits to send out into schools to show people what these kinds of solutions look like, to learn and explore the ideas of how does light behave and how is the physics of this whole reflective thing really working. And it can be done very hands-on. And I think the advantage of this is that it's showing, we have the ability to show people that this is not a threatening type of solution. So we have mirror kits to send out. We have a website that is almost ready to go online that is able to show what our sensors are bringing in and what these sites look like. And at the same website, you can also download lessons plans. And then we also have demonstration plots to show communities how these mirrors look and function.
All right, and that's about where I take over. Wanted to talk very briefly about what we've been doing so far and our plans for the very near future for testing the mirrors and their cooling effect. So we got our hands on a couple of the prototype mirrors last summer, and we're able to deploy them here in Plymouth, New Hampshire. And you can see some of the details. And yeah, we had 2 whole mirrors, but we were able to measure soil temperature in the shadow of those mirrors for a couple of months over last summer. And we also had a control plot where we're measuring the soil temperatures without the mirrors. And there's pictures of a few of us that were able to work on this over the summer and through the school year. So here's just a couple of the results. What you're looking at is the soil temperature on the top graph for about a 30-day period. The red line is the control and the amount of heating. And you can see the daily variation in the soil temperatures at a 10-centimeter depth. And the blue line is in the shadow of one of the mirrors. I believe it was the east mirror in this case. And you can see that there's definitely some cooling affected in the soils, which is what we're looking for. The bottom right picture is one of our students going and collecting the data. And you can see that the temperature anomaly, the cooling at both the 10-centimeter depth and the 25-centimeter depth is pretty significant on the orders of 3 or 4 degrees Celsius on sunny days. So that's encouraging. And that initial data is inspiring us to set out whole fields of mirrors to do some testing about those cooling effects. So next slide, Lisa. Here's some simulations that Ye and his colleagues have run that are showing sort of what the spatial distribution of the cooling might be with an array of mirrors. So the one on the left, the warm colors are actually the amount of cooling, so more cooling in the warmer colors, and you can sort of see how as the sun passes east, west, and north, south, that the shadow produced. And then the ones on the right are also showing that, you know, as the solar angle changes here in the mid latitudes through the year and the length of day changes, we're going to see some different cooling patterns along the ground And we're going to be trying to measure that amount of cooling in our experiments this summer. So that's kind of where we're at with the cooling simulations. Next slide, please. So we have two places in New Hampshire that we're going to be setting out some plots with mirrors. The one on the left is the local plot here in Plymouth, New Hampshire. And as Keza mentioned, or somebody mentioned, it is actually located right next to Plymouth Municipal Airport, which is a grass runway with several dozen propeller airplanes. But nonetheless, we are going to deploy there. We did have to get FAA approval for the mirrors to be stationed there, and that turned out to be not a problem. One advantage to this site is it is also about 500 meters away from an automated weather station run by Plymouth State University out at the airport. Down in Concord, we are right adjacent to the NHTI campus, and again, an open field right by that oxbow in the Merrimack River there. And just another place to have in a similar latitude and similar climate to compare the cooling associated with the mirrors. Next slide. So in Plymouth this summer, we will be setting out some mirror plots, and we'll be measuring soil temperature, soil moisture, atmospheric temperatures to try and actually quantify the amount of cooling from the mirrors. And at Plymouth, the experiment is really going to look at how closely spaced the mirrors need to be and how much cooling you get for different densities of mirrors. And that's sort of where we're going this summer. And we're going to compare our actual observations of cooling to the modeled predictions. And if we go to the next slide, down at NHTI, they are also going to be measuring with a similar set of instrumentation, identical set of instrumentation, the cooling for, once again, 49% mirror coverage. But in addition, we're going to be testing different materials and different mirror heights for some of the plots that will be at our field site at New Hampshire Technical Institute. So 1 meter high mirrors versus ½ meter high mirrors, using bamboo rods, using no mirrors or black glass instead of mirrors. So we're going to be testing a bunch of different materials and mirror heights beginning this summer.
Well, thank you so much. And we want to thank everybody who has presented today, as well as all of you who have come to become more informed and to learn about what we are doing. So we'd like to invite you that if you are moved to make a donation at MEER.org/donate, and I'm putting that link into the chat. And you can also contact us through our new website, which has recently gone live. We hope to see you all again next month on June 5th, when Leon Simons will be presenting on MEERTALK. He is a climate researcher and entrepreneur who's working on climate and energy. So stay tuned about all of that. And we really are so glad you've been here with us.